for any operator f, and then we use that. So we define what is df by dt, right? So basically you have to calculate the integral and psi star f psi, and then take the derivative. But this is the notation, and then this is what, some I by h bar, and then commutator or Hamiltonian with this. And then this we use to obtain basically time variation of the mu. You get similar equation like the classical equation. That's where we were. Then, if you recall, we said that ultimately we are interested in the fact that you have an AC field also, and the field we have in mind is something like this. So it's in some x direction, and then in this notation we have said this is hx0 cos omega t, but then this can be rewritten, so you can think of a hr and an hl, and basically sum of two will give you effectively this with some factor of 2, because when you add the hr hl, the sine terms cancel out, the cos terms remain, and then there's a factor of 2 and all that. So the reason to do this is in practice, this is what we'll apply. Okay, in practice you'll have a coil like this, solenoid coil, and you'll apply an AC current. Okay, it's only in that direction that the amplitude will change with some with some sinusoidal thing of this kind. So this is what you'll have in practice, but to work out, it's convenient to rather write this combination of sine cosine. So this is rather written as HR, okay, and because then there's a rotation matrix involved and all that. So this is in practice, in actual experiment, what you apply is this quantity. However, in working out this time derivative of moment and ultimately how the z component of moment changes with time, etc., looking at rotation of vectors, in doing all that, it's much more convenient to rather write, instead of this field, it's convenient to write, imagine this as a combination of HR and HL, where this is H1 I cos omega t plus j sin omega t, and so HL will be with a minus sign. Okay, so in reality, it's a combination of HR and HL which will give you this. So actually, in practice, you will need one field going this way and the other going the other way, right? So in order to generate this, so you will write it like this, and ultimately, one argues that you can just stay with the HR, and that's good enough. If in actuality you applied fields like this, then there is a, which I shared, so that's from Abraham, a couple of pages, where he says that the other, you'll be away by 2 omega from the resonance frequency, and there is an effect of that, and it has been demonstrated also with a very small intensity, etc. I've not looked at the original paper, but it's cited there, you can look at it. So you just replace the time dependent field. In actually it is this, you just replace it by actually this HR. So just the cos omega t plus sin omega t. Okay. And then your dmu by dt, this was the classical sort of picture where this was written as mu cross gamma h naught plus h1. Okay, and this h1 is basically the thing we apply along the x-axis, but finally, when to work out things, we write h1 vector as some amplitude times I cos, so these are HR, plus I cos omega t plus j sin omega. Okay, and then so this goes in here, and remember you want to write d mu by, this is again going back to the classical sort of idea that you want to relate d mu by dt in the rotating frame to d mu by dt in the other way, I mean inertial frame to rotating frame. So this is what is an inertial frame where you have this kind of complicated field, but you can convert it to the time variation in the rotating frame using this standard result. So any vector mu, if you want to look at the time dependence of this from some inertial frame and then relate it to time dependent the rotating frame, this is valid. We have done this. So you can, so this is again, we are looking at the classical sort of picture. You can use this and then put it back here, and one can then choose your omega as, you can rewrite this omega and minus omega z k, right? So that's our standard convention. Your z prime axis is always the same. Any rotation is about this quantization direction. So the h naught field is along the z axis, right? And then this is the sign we choose for this capital omega. So I mean, this is still sort of classical. We then will, you just put this back, you'll easily get that d mu dt in the rotating frame is mu cross gamma, and then you'll have a h naught minus omega by gamma along k plus h1 along I. Okay, so all the time dependent sign cost, all that has gone. Okay, so of course we understand that, right? So there's no more time dependence here because now we are dealing with what's happening in the rotating frame, and you can rewrite this as some mu cross gamma h effective. Okay, and then that's our usual thing. You can then, if you choose, so what did I written? Z, is it? So sorry. Mistake in notation. This I choose plus. Okay, my rotation is along the positive, so along the around the k axis. So that's my rotating frame with the positive value. But then I get the minus sign over here. Okay, sorry. This is also yeah. This is omega z k, and just in terms of the, so you will basically get here omega z plus gamma h naught, right? And when you rewrite this, you get omega z plus gamma h naught, and then after that we choose omega z equal to minus omega. Okay, where this omega is the precession frequency. Right. At resonance, if this is equal to gamma h naught, then this cancels out. That's what we are saying. So you can rewrite, if you like, only in terms of frequency units. So main point is that you can go to a rotating frame where you can nullify the effect of the DC field, and then you are reduced it to an equation where you have rate of change of moment equals mu cross gamma h1, and then now the precession is about the I axis. Okay, So this is the x-axis, and any precession is around the x-axis, around the direction in which you applied the h1 field. Okay.
Sir, in this cos omega t and sin omega t limit, that omega is a gamma h now?
Right.
That cos omega t and sin omega t.
No, not. I mean, in general your frequency is variable. Okay, it's you externally apply this, so it's in general variable. If it is equal to, so one should maybe write omega naught is gamma h naught, and in resonance condition then this is gamma h naught. Okay, so only in resonance condition that Z field gets nullified in rotating field. Right? These cancel only when this frequency of the RF field is actually equal to the resonance frequency.
So, why did we choose this sign convention? Omega is equal to minus of omega. Is it from the algebra that we find because we need to be along the same direction of rotation, right? Like if you want to nullify the effect of rotation in the rotating field.
So if we draw in terms of a picture, so this is my now Z component of the field. So this is my x-axis. So I have now my effective field is less than the, why the choice of minus, so let me just write it. So my this is now h naught minus omega by gamma. And this is my magnetic moment, this is how it is pointing. So I need to choose.
So at resonance, the effective field should not have any Z.
Yes, yeah. So actually, if you, this is that turns out with the algebra, I sort of skipped the step here. If you go back a couple of steps, this is what you want to expand, right? So d mu by dt inertial frame is this quantity, and then you need to add on omega cross mu and so on. So if you actually do that, you get d mu dt in the rotating frame as mu cross k unit vector omega z plus gamma h naught plus I gamma h naught. Because very simply, I have this as minus omega cross mu, so I can write this plus mu cross omega. Okay, and then therefore there's a plus sign there, and with the omega as omega zk, okay, I can then this itself is written like this, and so you'll have a gamma h naught plus, so along the k direction you'll have a gamma h naught and a plus omega z. So that's why you get a plus there, and so one must choose this with a minus sign to nullify. I mean, this should reduce the z component of the field. I mean, that's the way to look at it.
Sir, effectively we are doing the same thing what we did in classical. Like we are doing the rotational frame
Yeah. So this is still classical in a sense. We'll do the quantum mechanical part where you're looking at rotation of the wave functions and so on.
Okay.
Yeah.
This is still classical.
This is still classical, no?
Why we need it here?
Huh?
Like we
No,
are-
they just to again, concretize in our mind how things are behaving. We have rewritten
I think just in the quantum we'll need the expectation values.
in the quantum case, yeah. Right now we just got the expectation value of d mu by dt. Okay, so we got the equation correct. We need to get expectation value of mu z, let's say. Okay, and how that evolves with time. So these Rabi oscillations, we already know. So that's coming next. This just to recapitulate that in the classical case, in going from an inertial to rotating frame, this is what you would do. And the choice of field, RF field, is by considering two counter rotating fields, and then that gives you the resonance condition, and then you have an effective field along this direction. It's a combination because now H1 is along this time independent. There's a Z component, again time independent, and so net field is along this some direction. Okay, and that. So then you have some complicated motion. It's precessing like this around an effective field. But if you go to a resonance condition, then you reduce this to 0. Okay, then the effective field points along H1 is the field. So then you are going to have the magnetization points along Z, and then it's going to recess around H1 like this. Okay, so again, just to make a connect with experiments, for example, if you have some way of switching on the H1 field and then switching it off, okay, for those who are already doing experiment, I'll explain otherwise. So in an experiment, it's possible to, so the DC field you keep on always. You put the sample in a magnetic field, so this is always there. And plus, the sample sits inside a coil like this. Okay, so you can switch on and off a current that goes through this coil. Okay, so one can have no H1, and then you sort of flip a switch. There's a programmable switch. You can flip that switch. It gives a RF at some frequency, and then you can again switch it off. Okay, so what's going to happen? And if this is at resonance. Okay, so you start out with the magnetization along you have net polarization, right? So you start with something along the Z direction. This is turned on, so it starts precessing. Then it's off. Okay, so how much you turn this angle depends on how long this is on. So E, whatever the duration. So if you have it long enough such that it tips by 90 degrees, then the nomenclature is, this is given pi by 2 and of course pi by 2. Okay, and then this, now the precession frequency is what?
This is gamma H1.
Gamma, how much?
So effective.
So I say I'm at resonance, so there's no Z component of the field, so it is just gamma H1. So
X direction. I want to move करेंगे तो the X direction is H1.
now you have a field only in this direction, so it's precessing, and the precession frequency is gamma H1. I mean, we have the effect, right? So this will go away. You will just have d mu by dt is gamma H1i. I mean, the direction is just telling around which direction it will precess. And so the precession frequency is just gamma H1. So it will now precess at gamma H1 around the x-axis. And if you have it long enough such that it tips by 90 degrees, it's called a pi over 2 pulse. Okay, so this is called that's the nomenclature, it's called a pi over 2 pulse. If it's long, twice as long, you can flip the magnetization full 180 degree, okay, down, then it's called the pi pulse. So usually these, of course, depends on the gamma, depends on the H1 you can generate with what current threads the coil. Typically, this is several microseconds in a practical situation.
So this time also depends on like what is the material on which we're trying to measure.
Which nucleus? It depends on the gamma. Yes. And this H1 depends on your actual technical arrangement. You know, what's the, how much current are you passing through the coil? What's the geometry? Obviously, so because the H field here depends the solenoid, so the H field depends on the I going through, number of turns, all these things. So yeah, so this depends on which nucleus, and this depends on your technical arrangement actually.
So the loop which we set in experimental thing, that will be hitting continuously to bring it to pi by 2.
So in an experiment, what you always have to do is, see, after this we'll talk about later, these guys have done it, you have not seen this, but after this you should get a signal from the coil. How it actually happens is that you have tipped it 90 degrees and then RF is off now. But there is some linkage with the bath. So you have a sample, you have a nucleus which has done this, but it's connected with the reservoir, the lattice. So it's going to, now you have disturbed it, it's not equilibrium. It would like to go back to equilibrium.
Relaxation.
Relaxation. So this relaxation has to happen and this is going to go back like this. In that process, it's going to change the flux threading this coil. Okay, so by Lenz's law, it will give an EMF, so which you will amplify and which is what you will observe. So that's the NMR signal. Okay, and the signals generated are of course very tiny. You know, nuclear moments are small. I don't know, microvolts. One can calculate actually, depending on the gain of the amplifier, this and that, how much signal finally you get microvolt, millivolt, something like that you will generate. So, of course, the signal that you get is sitting on top of electronic noise. So, one shot is never enough. Usually not enough. Okay, so you need to average it over many shots. Okay, that you people have seen. So tens, hundreds, thousands, something like that. So I need to hit it with a pulse. You get some signal sitting on some noise. Wait for a while, again, add it to this again. So the random noise should even out and become zero, and the signal should grow. Okay, so this is what happens in practice. Was that?
Yeah.
That was your question, yeah. So it's sort of in a loop. I have a program running on the computer. It gives a RF pulse, looks at what the signal is, waits for a while, which I can program. Again comes back here. Again comes back here. RF pulse. Again this, and so on, until 1,000 shots are over.
So we set the number of cycles.
Yeah.
Exactly. Yeah.
So we are trying to bring it as close as possible to pi by 2.
No. It's already pi by 2. That you
Towards
did.
the H1 direction.
No, that you already did.
Okay.
You are now trying to get a signal from the sample. You figured out what the pi on to pulse width is, let's say. Okay, we'll talk about later how you can do it, but that's already figured out. Let's say it's 4 microsecond. Now, how to do a measurement? Okay, one shot is not enough because of signal to noise problem. So you need to average over many cycles, and that's what you're doing. What you're asking is separate thing. I'll come to later.
So this figuring this T pi by 2 is like what is done in calibration and
In a way. So how would you do it? So just so bring up this question. This is the first thing you want to do in practice. So again, just sort of symbolically, is sketch-wise. This is your RF pulse, and then after that there is a signal. Okay. So this is actually inside this is something like this. You have a cos omega t, right? So that's what it is. But usually you depict it as a some square pulse. And then the signal after that, again, that's also AC signal really. Okay, we'll come to the technical part, but finally you bring it down and observe in a DC by some mixing basically. So you get a signal like this. The name of this is called the free induction decay. After the RF pulse, the nuclear spins are now free to relax. Okay. So this is still not the spin going back to the z-axis. You actually have a collection of spins, and there is not infinite coherence between the spins. So with the, let's say, pi/2 pulse, you tip all of them by 90 degrees. But the xy components for different ones, so those changes will not be in phase. Okay, they are not coherent. So even here, up to here, you have not really lost the z component of magnetization, you just lost the xy components. And so they have gone out of phase, and so you are not able to sense a signal. So, there are sort of two decay constants: spin lattice relaxation, where you are losing energy to the lattice. Then there is a spin relaxation, where you lose energy between the spins. So this is largely that. Okay, T2, spin relaxation. So the signal that is generated, it decays because of spin relaxation, inhomogeneity of the fields, because you have dipolar fields of nuclei. So the applied field plus dipolar field, or somewhere else applied field minus dipolar field, depending on where you are, right? You have a spin here, you have these paramagnetic nuclear spins, and then with the RF pulse you have tilted all of them. So you start out with, let's say, all of them like this, and then they will eventually go back to z-axis, but the problem is, so H0 is still there, right? So H0 is there. Now, as time passes, note that at this side, there is an applied field plus some local field because of dipolar field because of neighbor, and that may be different at different sites. And if you just look at near neighbor or something, and so you will get a decoherence. Okay, so therefore this decay. So the upshot of all this is that you have a RF pulse. Once you stop, you get a signal. There's some maximum, and then it decays. How much this is depends on how much you tipped it. Okay, if you tipped it by 90 degrees, that's the maximum flux change that it will give rise to. So you get a maximum. If you didn't manage to tip it maximum by 90 degrees, then you'll get a smaller signal. So the calibration part, as you say, is first thing you want to do is you want to try. First, keep this 1 microsecond, check how much signal you get. Keep it 2, 3, 4, and plot that as a function of this pulse width. What should you get? If I want to plot height of FID as a function of pulse width. Okay, so when pulse width is 0, of course there's no signal. Okay, as I increase the pulse width, it should maximize. What happens if I give a pi pulse? XY mein there is 0. Okay, so this is pi pulse. Then I can also get it in the negative direction. So it should just continue like that forever. Okay, so that's the first thing one should normally do. You do a test, you put the sample, and then you have generally some idea. It's not going to be 100 microseconds usually based on experience. So you do a measurement of the signal size as a function of pulse width. In our spectrometer, it's done automatically also. You can set up a sequence where it runs 10 scans with 1 microsecond, then another 10 with 2, another 10 with 3, whatever. And then ultimately you put the result in a file, then you check, and then if you find something like this, okay, then this is what my duration of, so this may be some 3 microseconds. So I figured out what my pi/2 pulse is. Okay.
Generally we don't do FID.
So I'll come to that, but you can easily do also.
FID is very short, like some microseconds.
No. In some cases you can see it. It's not a problem.
If the
So
T1 is higher, then one could see the FID.
So there are some technical problems here. You can see when ADM and you can see FID. But I'll tell you what the technical problems are. So one very quick way to estimate the pi over 2 pulse width if the signal is good is check for what pulse you get zero signal. Half of that, of course you might have overshot it all, but you take care of that, but half of that is your pi over 2 pulse. So you can easily get a quick idea of what the pi over 2 pulse is. But you should plot, you should get a sinusoidal variation.
So even while doing plotting this graph, one needs to do a few, like you mentioned for the other, we need several cycles.
Yeah, absolutely, yeah. So 100 shots here, 100 shots here, and so on, and then you plot. Yeah. So if the signal is very weak, this itself will take quite a while. Yeah. So some combination of what the classical result is, what actually happens in experiment. So again, this comes later, but since you asked and these people already know it, so this is what you would like to do. Okay. Now, practical problem is that you are passing some current. Basically, it's a high voltage that is applied to the coil. You want for various reasons I explained, you want to minimize this pi over 2 pulse. So only way is how do I maximize my H1? How high a voltage can I give such that this is small value is achieved and I can do my experiment. So in practice we use only one coil that serves as a transmitter coil as well as a receiver coil. In the old spectrometer there were actually two separate coils orthogonal to each other. So the transmitter signal went to only one and the induced EMF and all was in the other coil which you measured. But for long now it's only one coil which is used. So practical problem is you are giving kilovolts usually, okay, hundreds of volts for sure. So of the order of kilovolt you are applying on this coil, and then remember these are just several microseconds, and soon after you want to see what signal is coming from the coil, which is maybe usually microvolt or something. Okay, so same cables are running, so I'll explain this later in terms of the practical aspect, but a quick sketch might help also. So you have a transmitter, okay, and then that is giving your, so this is the sample coil and so on, and in a DC field and so on. Okay, here's my coil like this, and I have my receiver, and through the same cable, so I want when the transmitter is on, this should be the direction, and I should not blind, kilovolt should not flow into the receiver, it will destroy it. So I want direction only like this, nothing going here. Likewise, after the RF is off, then nominal signal is going like this. I want this isolated. I don't want the microvolts to go here, and I just want it to go to the receiver. So lots of different tricks are used. You can use diodes. Okay, so you can use diodes. So at small, so here for example, series diode. For others also, you can use series diodes here. This is AC that is going, right? So you can use it series diodes like this. So high voltages here, this will short circuit, no problem. Signal goes like this. But microvolts coming from here, the diodes are open, so nothing will go here, everything will go here. Likewise, here you can put again diodes. Grounded, perfect. Yeah, you can join us and do experiment. So when you have high voltage, this will see a short side will go grounded. When you have microvolts coming here, this will see as open, and then good, everything goes to the receiver. Another thing you do is you use, what do you use?
Mixer.
No, mixer is a separate thing in terms of cables and all.
Cable.
Amplifier.
You use
Yeah.
lambda by 4 cables, so that also helps. It will see one as open circuit. The standard trick. If you have, just check oscilloscope, and you connect so RF synthesizer, and you just, so that is connected, and you just have a, at that frequency, cable of length lambda by 4 open circuit connected like this. Okay, so this will act like a short circuit. You will not have see any signal on the oscilloscope. It's a crazy thing. Okay, so that's the function of this lambda by 4. So you have all these tricks in order to minimize any transmitter RF going to receiver and maximize sample signal going to receiver and nothing going here and all that. So by the way, usually you have a diode bank, not just two, many pairs, because some might fail. So likewise here. And of course receiver is not one, there are different stages of receiver amplifier. You know that. So in spite of all this, still after the RF pulse, for some time the receiver is dead. Okay, its kilovolt has gone for a while, it is dead. This is nominally called a dead time. Okay, so in this pulse sequence, you have this RF pulse, and what you expect is some signal like this from the sample. In practice, you may be dead in this region. Okay, depends how fast this falls. If it's falling in less than 10 microsecond or so, then you are within some dead time of the whole setup. And so you can only see this part of the signal. Okay, this one is lost. Okay, so this is what you're saying. So very often nowadays we don't look at FID. Why struggle with all this? Is there some way to shift this signal further? Okay, so this again will come to later, but it turns out there is. You give one pulse, and okay, this is the signal. So this is my 5/2 pulse. So I flip it by 90 degree, then you get this decoherence. So then they are actually precessing. In the lab frame, they're precessing about after the RF is off, they're precessing about the H0, okay, like this, in the XY plane. After that, I give a pi pulse. So they're already in the XY plane, and what's happening is that this has died down because there's a lack of coherence. So they are all precessing, but then some are precessing slightly faster, some are precessing slower because local fields are different and so on, homogeneity of the field, etc. So some are slower, some are faster. So this one is faster, this one is slower. So slowly the angle will keep increasing, and I get a decay of the signal in the XY plane. If I now flip by 180 degree, then it happens the other way. The faster one will have moved, it will 180 degree around that axis. So faster one is here, slower one is here. So faster will now overtake the slower one. Exactly after how much time you waited. Okay. So this one I have shifted to. So if this is some t, then after another t, I can refocus, and I can basically whatever I had here will appear over here, and now I'm out of the dead time of this pulse. Okay, so this goes by the name of a spin echo. It's an echo of the FID. Okay, so this is what we actually do in experiment. Rather than doing a single pulse and all that, we use two pulses, one a pi/2, then a pi, so that you can shift the FID to some later location. So the dead time may be here, no problem, we are out of it.
So and the dead time is fixed for any pulse width?
So it depends on the quality of your receiver amplifier. There are some other ring down problems. So you can get acoustic ring down of so the coil, because of the large RF, can vibrate also. So even that will give some oscillation, which is not an NMR signal. There are ways to get rid of that, but you might have still some remaining. Okay, so always good to be able to shift this to a later time location. Okay, so yeah, what does the dead time depend on? Basically, newer and better, more expensive receivers will have a smaller dead time. And
so, why at all do we have a dead time? I mean, when the kilovolt pulse is applied?
Yeah, so in steady state all is good, but I think in transients, just when you have large pulse coming, and so for recovery, these are supposed to be fast recovery amplifiers, but they are not infinitely fast. They have some recovery time. The problem of the transient. Once everything is steady, then it's okay.
No, so is it like somehow the receiver is sort of cut off from the circuit for that amount of time? Is it something?
Yeah. So absolutely. So it's likewise for the transmitter also. So in order for it not to give unnecessary output, there is something called actually not blanking but unblanking pulse. So even before this is given, you give an unblanking pulse. So before this, the transmitter is really zero, blank. It's not outputting anything at all, and no way. I mean, even the noise, nothing. It is stopped. So the programmer gives an unblanking pulse. So it just goes from 0 to 1, and that usually we want, depending on the receiver, 1 microsecond before the pulse is to come. So it's sort of telling the transmitter after another microsecond, expect to output a large kilovolt. Okay. So at least up to here the receiver is fine. And likewise, after the pulse, again this goes down. So again it blanks out. So to the extent possible, you try to arrange all these things so that no leakage into the receiver of this large signal. Still, after all that, so usually in this setup, you have some cable length. So signal always, of course, decays with longer length. Anything, your computer Ethernet cables also, longer the cable, you'll have a decay of the signal. So you need boosters periodically. So you get a decay of the signal to, again, guard against that. Very close to this, one puts something called a preamplifier. So before anything else is done, you already get it to a high level and then do whatever electronic massaging, etc. later. So there's a preamplifier here. So again, you need a fast recovery preamplifier. So again, it's just an issue of quality of this preamplifier and amplifier which determines this dead time. And other things, your lambda before correct, and these diodes. So mostly all technical things. And so you can get down to a few microseconds. So even since we are talking about it, you cannot make this T very large and still expect the same value of the signal. So this decay here is, firstly, there are two contributions. So there is a so-called T2 star, which is because of this inhomogeneity of local field which cause decoherence. But then there is also inherent T2, intrinsic spin-spin relaxation time. So no matter this inhomogeneity, etc., that still remains. Okay, so there is still a decay of this signal with a law as n0 e to the power minus t by t2. Okay, so if you have this, just to do a comparative, if I have, then my echo is here. Okay, so let's say this is roughly equal. If I rather, then my echo will be here. Now this will be smaller. Okay, so if I just superpose, this is going to be here. So this will go down exponentially. So in fact, that's a way to determine T2. You set up a program where you vary the duration between these two and measure the height of the echo as you increase. And then fitting that, you get a spin-spin relaxation. Okay, this is what we normally do. Again, this can be put in an automated program where you can delay table which automatically varies 10, 20, 30, whatever you want. And then records the spectrum for each, and later you analyze and then.
So why T1 is not playing any role here? I mean, it's just energy distribution between states.
Because you're not going long enough in time. In usual solids, the T2 is of the order of tens or hundreds of microseconds. The T1 is millisecond, second or more. So it's just an issue of. So we'll see block equations where you have these two relaxations separately phenomenological, but this is what it is in practice. So this is how you determine T2, and then we'll see T1 how to determine also. So by the way, in this scenario, the signal here is actually like this because this is pi over 2 pulse, and if you have a good pi pulse, the signal here is 0. Yeah. Anything else about, there's a mix of some technical things and what you actually do in the experiment and so on, which I'll talk about later also. So in a practical spectrometer, you can vary the, nominally you can say you can vary the power that you are hitting the sample with. No? So the H1, that you can vary by, you can play with the amplitude of this RF. So in our spectrometer, this goes by the something called F1 amp. So what is the amplification of the transmitter? Okay, nominally you put some numbers 10, 15, 20. So whatever they mean, you need to actually do the experiment to gauge. So you can do two things. You can keep the pulse fixed. Okay, this is fixed, pulse width fixed, and vary this to figure out the optimum condition for a, where you can tip it by pi over 2. Okay. This also can be done automatically. Or you can do the other way, keep this fixed and vary this to figure out what is the correct pi over 2. So either way, if you have power too low, then the duration is going to be long. You don't want it very long. So the reason I explain later maybe. So usually you would like to fix a power such that this is several microseconds. Okay. So ideally, as you might realize, why can't I just make it even higher, such that this is really small? Because there's some advantage in having very short pulses. Practical problem is you have a high voltage, very high voltage on the coil. It can even cause dielectric breakdown. So you have a coil and then you have a ground as the cryostat, and high voltage can just cause dielectric breakdowns, lightning passing from there to that. So you lost the RF. It's not going into the exciting nuclei in the sample. It's just gone. So there's sort of a practical limit. What to do? So we have 1 kilowatt amplifier, and with these, so although we don't run it at maximum power at all, because you cannot. So, but ultimately we get several microseconds, 5, 10, 15 microseconds for the typical pi over 2 pulse rate. So in practice, if you find that there is some signal loss and there is this technical issue of arcing, then the thing to do is decrease the RF power. Then maybe you have to play with longer pulses, but that's okay. At least you'll get a signal. Yeah, then we want basically now a quantum mechanical description. No? And at least get started on this. So our final result I'll write down already. What we get finally, we want solution of this dmu/dt equation basically, right? So this time dependence of the z component of magnetization expectation value is what is at 0 times cos gamma x1. Classical answer we have written down. It's precessing about this h1 axis with this frequency. You can call it omega 1 if you like. But we need to, quantum mechanical description, we need to get this answer. So this is our final result. And so, we just say what the result is. Result is that if you start out with the magnetization fully along the z-axis, it will keep, as long as the h1 is on, it will keep doing this. So population of from plus half to minus half to plus half to minus half will keep happening forever as long as the h1 is on. These go by the name of, which you might have learned, Rabi oscillation. Okay, so a part of the cycle, it's absorbing energy from the RF, going from plus half to minus half. Then the other half of the cycle, when the nuclei come down, it's actually giving off energy. But so this is the final answer. This is what we need to ultimately get. So in order to build that, what we are going to do is basically write down, time dependent, so rotation of spin operators and so on. Let's at least get started. So some things which are relevant. So this I already said. So if you have a Hermitian operator, I called it F, right? Then you have phi star F psi d tau is, of course, F phi star d tau. The other thing is you are familiar with when you write the Heisenberg form of the time dependent Schrodinger equation, so I h bar d psi dt equals h psi. Okay, now Hamiltonian psi. So the time dependence of the wave function is e to the minus I Hamiltonian t by h bar psi 0. Okay, so when you operate that on something, you need e to the power some operator trying to operate on various things. You know how to do that? So you exponentially have to express as a series, right? Power series, and that you apply. So that's what it is. So you just recognize that e to the z is 1 plus z plus z square by 2 factorial plus z cube by 3 factorial and so on. And likewise, you can write e to the if similarly. Okay, and so f is your operator. So if you need to operate e to the if on something, then all you need to do is you write this as 1 plus if plus again if square. So signs will keep changing, 2 factorial and so on. And if you want to operate this on the wave function, then it amounts to operating this on the wave functions. Basically, finally, you'll have the eigenvalues. If this is the eigenstate, then you'll have eigenvalues in the exponent and then multiplying the wave function. Right? This you're familiar with. So, of course, if f is Hermitian, then e to the if is not, as you can demonstrate. Right? So, if f is Hermitian, then e to the if is not. Because the signs will change, and when you do e to the minus if and all, it will not be the same. Okay. A couple of other things which maybe as and when we need, we'll write it. Okay. So if need it at some point, if A and B operators commute, then A e to the IB is e to the IB. Okay, and also e to the I A plus B is e to the IA. Okay, if only if A and B commute. So we will need this kind of thing. We'll have the Hamiltonian here getting the spin operator, something else here, and then we need to be able to interchange and so on. Right. So now back to this spin. This is sort of general. Back to spin in a magnetic field. Nuclear spins in magnetic field. Our usual starting point is I h bar d psi dt is h psi, and we write that the solution is time dependence e to the minus I h t by h bar psi. So for a spin in a magnetic field, we know what the Hamiltonian is in I, nuclear spin I in a magnetic field. Let's say H naught to start with. We know that this comes out to e to the I omega naught t I z. Sorry, 0. And of course, Hamiltonian is minus gamma h bar h naught I z. So, of course, omega naught, our usual notation is gamma h naught. So, h naught, I mean, one can intuitively also see from here, h naught, this DC field, actually produces a rotation of the magnetic moment. Right? So, this wave function at a later time is the same magnitude but with a different phase factor. So, it's basically this is some angle, and so it gets rotated by that angle depending on what time you are observing. Okay, so that picture is still there. That wave function at a later time is because of rotation of the spin, because of the applied field actually. Okay. And so again, the notation is that we take omega is minus gamma h naught. Okay, that so this we call a negative rotation. So you know, wave function psi t is obtained from psi naught. By this negative rotation. Okay, so this is just a choice that we have.
Initially, we had chosen omega z the classical case.
Yeah, but remember there was a
We finally got
we needed a minus sign in order for the two to cancel. So yeah, so that's sort of the sense. Yeah, or also here you want to look at, so wave function has a negative rotation, or the operator has a positive rotation if the axes are fixed. So those are the two equivalent things you have in mind. Okay, so we then want to write down this expectation value of operators to these rotations. No? So what is Ix? Right? So we want to know ultimately this expectation value of time dependent moment and time dependent expectation value of I and so on. So this is what we want to calculate. So now we have time dependent wave function and then this Ix sitting in between, okay, and this is what we want to calculate. Okay, what we can do now is write the wave function as wave function at 0 times some rotation, right, just as we wrote a little while back, and rewrite this, which then looks like this. This can be written as psi star 0. And then I have e to the minus I omega naught t I z Ix e to the I omega naught t I z and this psi 0 Okay, so in this expression, so this is what is expectation value of Ix. In this expression, all the time dependence is in the wave functions. By rewriting the wave function time dependence based on what we wrote a little while back, this thing here. right? So psi t is psi 0 e to the I omega naught t I z. So psi star will have a minus sign, okay? And so using this, we have now separated out, so written it as time dependence only in this part here. And this thing I will call some Ix prime. Yeah, exactly. So all the time dependence has gone into the operator. There's no explicit time dependence for Ix. But now having it like this, there's a time dependence over in the operator. Okay. So you can. So there are two equivalent descriptions. In one where I is fixed and the wave function rotate in some sense, and this other one with Ix prime. So you have now psi star 0, Ix prime, psi 0 d tau. Right. So this describes a fixed wave function. Okay. And then the operator rotating in a positive sense. In this case, by our definition, this was rotating in a negative sense. And so here the operator is rotating in a positive sense. So the next thing, yeah, we can still do 5-10 minutes. We want to basically ultimately write down what is d mu by dt, right? So we need to take, so like what is dIx by dt, diy by dt. This is the kind of thing we want to write down. Okay, and then solve that to get the time dependence. Right? That's the intention. So let's this integrand on the right hand side, this part here, let's call that f. So my f of phi, so where there's a rotation of phi involved, is e to the minus I z phi Ix e to the I z phi. Then you can do df d phi. If you fairly straightforward to do, all the phi dependence is over here and here, so you get two terms, right? So you will get Iz Ix and then Ix Iz, right? Yeah, and so you will get a commutator of Iz and Ix, so that will give a Iy, right? I square root of minus 1 Iy. So this is equal to e to the minus I Iz phi Iy e to the I. Because anyway, when you take a derivative, this small I will also come down. So, and in the commutator, that will bring another small I. So those will multiply and ultimately you will get this. Okay. So df d phi means you are taking derivative of this x component, that gives a Iy. You take a second derivative. Again, you do the detailed algebra, but again it's sort of easy to see. What you will get? You will get the commutator of Iz Iy now. So back to Ix. Okay. You keep the signs properly, you will get plus f equal to 0. D square f by d phi square plus f equal to 0. Right? You take a second derivative, you get commutator of Iz Iy, which is Ix. So basically f. Okay, and keep the signs clean, then you will get this. But this solution we know, some sine cos combination, right? Similarly, so a cos phi plus b sin phi. Okay. Similarly, you can do. So okay, so f is a cos phi plus b sin phi. and F0 is of course A, and F prime 0 is of course B. And depending on your conditions, but also F0 is also Ix, isn't it? So at zero angle, right? So F0 is Ix. Right, so F0 is also Ix, and F prime 0 is Iy. Right? So this is in fact Iy. So I actually have this A can be, so I have Ix cosine phi, Iy sin phi, and left hand side is what? Ix prime. Right? So Ix prime, right? That's how I defined that. Right? Where the time dependence or angle dependence is in those exponentials is actually Ix cosine phi plus Iy sin. You can likewise work out what is Iy prime, right? So straightforward. I will do a new function where you have Iy here. And once again, when you take derivatives and all, you will get commutator of Iy, Iz, which will give Ix, and then another one will give back Iy. Okay. So similar equations you will get, and one can again simplify. So you can get Iy prime is just minus Ix cos phi plus Iy sin phi. So it's just the rotation matrix, right? From Ix Iy you're going to Ix prime Iy prime. It's just the, and Iz nothing. I mean Iz prime is Iz, right? So that's evident.
That the minus will be with the sign, right? If it is a rotation.
Sorry. Yes. So it's Iy prime minus Ix sin phi. Sorry. Correct. Minus Ix sin phi plus Iy cos. Okay, so we have come to a point where we are basically saying that Ix prime, Iy prime, Iz prime are just obtained by rotating Ix, Iy, Iz about the common ZZ prime axis. Okay, and then might as well spend 5 minutes and finish this part. So basically, e to the I, Iz phi, this generates rotations. You already know this probably, but that's what it is doing, right? It's generating rotations. So, okay, now we need to use these things back into the Schrödinger equation I bar d psi dt equals h psi. So there, okay, maybe next class. We still need to do that. So for that, it's useful to, again, you have this I plus equals Ix plus Iy, and I minus is Ix minus Iy. You can also write Ix prime plus Iy prime. Okay, this works out to, you can rewrite Ix prime in terms of the sine, cosine, like that. And so if you work this, this comes out to I plus e to the minus I phi, and likewise if you have a minus sign here, then it comes out minus okay, so this next thing is maybe we'll do next time. we need to go back to the, again, Schrödinger equation and rewrite where the time dependence has gone into these operators, where we have now defined these x prime, y prime and all that, and then get the final answer. You won't find the time dependence of mu, but you can see it from a rotating frame. Okay, so in mu prime, I prime, I x prime, I prime, I z prime. That's what you want. That's in the rotating frame basically what's the equation, dynamical equation. So by using these, we'll do that maybe next time. Then after that, maybe after that is phenomenological, these block equations. So once you have now tipped the magnetization, what happens? Already we have said it that you need the spin relaxation and a spin lattice relaxation. So block was the first one to sort of very intuitively write it down, and then it's still used that standard form. Yeah, so I stop here. Let's see when we Wednesday maybe, yeah.